Chapter K, we're going to look at inverse functions. Now, what I'm interested in doing as we take derivatives of functions that we know, I want to be able to handle the inverse function for the sine, which is the arc sine. And I want to have a general way to approach the inverse of functions, like the tangent, cosine, for example. So what we're going to look at is a simple linear example to get this concept of inverse function understood. So take y as a function of x. And here, remember, a function, you have an input x and you get one output. You could have different values for x to give the same output as long as you only have one output. And we're going to take a very simple case, x plus 1. And the question we're going to ask is, what is the inverse function? Now, the inverse function I'm going to call g of x, and we can also write that as inverse function of x, like that. I want to find this two different ways. Method 1, we're going to solve for x, because remember, for inverse, you give the y, then out comes the x. So for the regular function, the f function, I'm going to put in the x, and then out comes the y. All right, so in that case, we solve first. We're going to solve first, and then what we're going to do is we're going to swap x and y. And I'll explain why as we get there. So if we want to do the reverse, we solve for x, so x would be y minus 1. But if you want this function in standard form, where you have the independent variable to be called x, we have to then do the swap. So here, before I do the swap, I'm going to say x, just to emphasize, is the inverse function of y. So in other words, you put the y in, you're going to get the x. And we can call that as the g of y, because it is a function of y. So this is very, very clear when you do it this way. You give me a y, and I'll give you back what the x is. But then to put it in standard form, where you have some function of x, we then just simply swap x and y, and we have then y is the inverse function of x, and g of x equals x minus y. The way you should think of this is that when you have something like g of y is y minus 1, I can make this anything. I can make that s minus 1. I can make that w minus 1. So making it x minus 1, it gives us the inverse function we were looking for, but in the standard form. And the advantage of this is I can plot it on the same graph, y versus x. Now, another way to get it quickly, depend on your preference, is you swap. We swap first. So in other words, we have y equals x plus 1, and by swapping first, we would have then x is equal to y plus 1. And after we swap first, then we solve for the y. And then we get y is x minus 1. And that is, say, the inverse function. We have it. So whatever preference you like, they see them both ways when you look at text. We can solve for x first. X is y minus 1, and then we swap the variables. Or we can rename them first and then solve. So you swap first and then you solve. And in this case, you solve first, then you swap. Okay, so now we're able to graph these on the same plot. So here we have y, and here we have x, and we'll look at here 1, 2, 3, 4, 5, 1, 2, 3, say 4, 1, 2, 3, 4, 1, 2, 3, 4. So the function f of x, which is our original function, f of x is x plus 1. All right, that's up here, at x plus 1. So that would be applied if x is 0, you'd have a 1. And if x is 1, you'd have a 2. If x is 2, you'd have a 3. So you'd basically have this sort of a graph going like this. Basically y equals x graph here, that's moved up by 1. Then if we look at the g of x, the inverse function, that's going to be x minus 1. So when x is 0, you're down here. When x is 1, you get 0, you're up there. And then when x is 2, you have 1. So you have this straight line that's parallel to the other one. Now, the nice thing about the concept of the inverse function is that we can look at this as a reflection about the y equals x line. So here's y equals x, and this is a reflection. You can consider this y equals x as a mirror. And if you stand in front of the mirror, you're going to be, see, your image is going to be the same distance behind the mirror, the image. And let's check that the inverse does work. The point we're going to check is x equal minus 1. So we're going to check this. If x is equal to minus 1 on the blue plot, minus 1 plus 1 is 0. So you're going to get here, f of minus 1 is going to get you 0. Because x is minus 1 plus 1, you get 0. And if you want to see where that is, if x is minus 1, would be over here, minus 1, minus 2, minus 3. This is 1, 2, 3, 4. 1, 2, 3, 4. And this is minus 1, minus 2, minus 3, minus 4. So when x is minus 1, you're at 0. Your y, or your height is at 0. So now what we do is we go to the inverse function, and for the inverse function, if we look at 0 and put the 0 in for the inverse function, we should get back what we started with. So the inverse function here, put 0 in, 0, you get minus 1. You get back what we had originally. So with the red graph here, at g is 0, you get that minus 1. You can see this is the reflection. If you're standing in front of the mirror here, there's your image right behind the mirror. It's a nice physics example there. So what I want to emphasize is the reflection about that line y equals x. So now we're going to move to something a little more advanced, and that is a parabola. So I'm going to look at a parabola. And the parabola that I'm going to use is, let's go ahead and put some values down, 2, 3, 4, say 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So here we have, 1, this is 1. I'm going to have the parabola here for the f of x. We're going to pick the f of x to be equal to x squared plus 1. So if I take 0 for x and square it and add 1, I'm going to be here. If I put in 1, 1 times 1 plus 1 is going to be 2. And if I put in 2, 2 times 2 plus 1 is going to be 5. So that's 2, 3, 4, 5. That'll be up here. So this will be the parabola. And on the other side, if I have here negatives, I'll get the same values, pairs. So if I have -1, when I square it, I get 1, and I add 1, I'll be back up to here again. And then here, if I square -2, I'll have a +4, and that'll get me up to the 5. So it'll be the parabola that you can think of it as y equals x squared lifted by 1. So now if we look at here, the y equals x line for the reflection and try to figure out what the reflection is, we could say here that if we go up 1 here, we'd be going up 1 this way. So we would be there. And if we look at how this goes up like that, this one's going to go more like this. All right. Now, to be more specific here, let's look at this point. This point is 2 and 5. So if I want to get the reflection right, I'm going to swap those. All right. So that would mean I would go 1, 2, 3, 4, 5, and then go up 1, 2. It would be up here. See, a way to help me get this reflection right, and then over here, I would have something that's going like this. But now I have a problem, because when you have a function, when you have an x value, you can only have one output. And here I would have 2 outputs. So what I do to solve this problem so that that parabola can have an inverse, I'm going to just throw this away, because I'm going to throw that away. There's going to be nothing over here to reflect. So I'll lay this part on the right side, and at the 0 point here, when x is 0, that is going to reflect this way. And that's going to be the inverse function. Well, how will we figure out the inverse function? Well, let's do it using the way that we had looked at earlier. We can say here, I'm going to go ahead and swap first and then solve. All right, so if I swap first, then for the g of x, all right, so here, for example, we have this function. We have y equals x squared plus 1. And then if I swap, I'm going to have here x is y squared plus 1. And then when I solve for the y, I'll get the g of x, because the y would be the g of x. And that would be here, solving for y, it would be a square root of x minus 1. So here is the square root of x minus 1. That should be what this red graph is. All right, so just to emphasize that, I'll put it in red here. And let's check it. So we had 2 and 5. You put in 2 for the f of x function, and you get 2 times 2 is 4, plus 1 is 5. So now here for the g of x, we're going to put the 5 in, see if we get to 2. Well, if we put the 5 in, we have 5 minus 1. That's 4. Take the square root, we get 2. It works out. And notice that, to emphasize here, I didn't take plus or minus the square root, because that would have then given me an ambiguity, wouldn't have a function. I just have the plus case. Let's consider another case. Here you have 0 and you get 1. If I put in 1 here, I get 0. And let's do one more. Suppose I put in 1, I get 2. 1 times 1 plus 1 is 2. If I put the 2 in, 2 minus 1 is 1, I get 1. So this is the inverse function, so you can graph them on the same graph. That's the reason why we like to do this, the relabeling, right? So we can plot them both on the same graph, but you just have to be careful that when you say come up here for the 2, 5 point, that corresponding point to get you the original value back, that's going to be, swap those 5 and 2. That's going to be this one, say 5 and 2. And that's the mirror reflection of that other point. Now, we're going to be using this to take derivatives, but watch. The derivative here is 0. The derivative here at the corresponding point is infinity. So what's going to happen is, if I look at the derivative here, the derivative of here will be the reciprocal. And that makes sense because what is a derivative? A derivative is a rise over the run, but when you have a dy over dx for the blue one, and then if we're going to do a swap with the variables, and we look at dx, say delta x over delta y, for this case, you're going to be looking at a swap. Now, it'd be nice to just check this, say the long way, for this point, say 2 and 5. So the derivative of the f function, that's easy. The derivative is 2x. Now the derivative of the g function, which is the inverse function, well, you take the derivative of this thing, what would you do? Well, you look at this as x minus 1 to the 1/2 power. For the derivative, you would pull down the 1/2, and then you would have x minus 1 you would subtract 1, so 1/2 minus 1 is negative 1/2, and then you would take the derivative of what's inside, with dx dx is 1. So the answer here would be 1 over 2 over the square root of x minus 1. So now let's check the derivative of, I'm going to call these like conjugate points. So for, say, 2 and 5, which is relevant for the f function, the derivative is going to be, you would put the 2 in. Look at the point 2 and 5, would put the 2 in for the derivative, and you would have the derivative is 4. So here, what I'm looking at for the conjugate point, so to speak, I will be looking at 5 and 2, that's the point, but I'm interested in plugging in the 5 in there. So when I do that, say for the 5, and just to emphasize here, you could say here, this is plugging in the 2, right, to get, say, the 4, all right. So then I would have here 1 over 2, 1 over the square root of 5 minus 1, and this would be 1/2. This is square root of 4, so 1/2. And sure enough, this is the reciprocal of the 4. It's 1 over 4. So this has a derivative of 1/4, and this has a derivative of 4. Now let's see if I can more formally establish this idea of the reciprocal. So let's start out here with a given. Let's have a given, y is f of x. So it's given that y is a function of x, and then if I want to get the x back, the inverse function, I put the y value in, I'll get my x back. And let's not do any relabeling here. Let's keep this very, very basic and simple. So now what I'm going to do is I'm going to take the derivative of x with respect to x. So the derivative of x with respect to x is going to be 1. And then I'm going to use the chain rule here. The derivative of g with respect to y, and then dy dx. All right. This is going to be 1. And look at this trick. This is going to show me that the derivative of the inverse function is equal to 1 over the derivative of the function I started with. So now I can put this function here with this f of x, just to have a sort of a consistent notation like this. And this is the intuition we saw earlier with the delta y over delta x can be thought of as being 1 over delta x, delta y. This is, and you take limits, this is basically a similar statement. And we could have dx over dy is 1 over dy dx. You basically flip it. So that's what this is basically saying, because the delta x, when you take the limit, that's the d of the g, the inverse function with respect to y. And this is then 1 over the f of x, the original, the y with respect to x. So we have this nice result that's going to help us take derivatives of inverse functions. So let's write this out with a little abbreviation. G, now that little prime there means you take the derivative of whatever the argument is. So that's how you would write this in shorthand notation. And that's 1 over. And this would be whatever the argument is you're taking derivative of. So that's what this is. And this is very, 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 very key equation. But you could also think of this as, since the g of y is x, you can also think of this as dx dy, because remember the g is x, and you're taking the derivative of the x with respect to y here, and that's equal to 1 over, and this would be the derivative of y with respect to x, since the f function is the y. So this is a little tricky to see all this stuff, the swapping and things, and so just go over it again. I mean, it's all laid out here. These are the summary equations here. You can think of this as the main equation,